My name is Maureen Conti, and I'm the principal investigator of the Oceanic Flux program. I'm a faculty member of the Bermuda Institute of Ocean Sciences. Bermuda has been a focus of oceanographic research for over 100 years. And the Bermuda Institute of Ocean Sciences, formerly the Biological Station, has been the host and the logistical base for much research over these period of years.
Okay, here we go. Wait.
So one of the most important things that we've discovered about the deep ocean since the time when the Oceanic Flux program first began in 1978 is that the deep ocean is really not a constant place at all. The deep ocean has seasons, it has weather, and this is one of the most important things that we've found out, that we can actually study. What's the weather like in the deep ocean? In fact, we don't have a word for it, so I call it the climatology of the deep ocean. Because the deep ocean, rather than being totally constant, which is what we thought previously, the deep ocean is really remarkably changeable. Sometimes nothing is happening. There's just a slight rain of particles, nothing too much is happening here. And then other times, depending upon the confluence of what's going on in the surface oceans, what's going on with the physical environment, the eddies, we can get rainstorms. We can get huge fluxes of material into the deep ocean, very fresh material. And that very fresh material is really important as a food source. And it's also very important because it carries with it materials and elements that are normally easily redissolved. And so there's a very important these understanding what's causing these rainstorms. Just like understanding, a meteorologist wants to understand what's causing these big rainstorms in the atmosphere, we're trying to understand what causes the big rainstorms in the deep ocean. The deep ocean is also affected by big storms. And so we have a wonderful record here offshore Bermuda of what was the effect of the storm, the Hurricane Fabian, which occurred in 2003, and also several other hurricanes. And so because the Oceanic Flux program mooring, or the sediment trap mooring, is out here continuously, we are out here when it's impossible to have a ship out here. So we actually recorded a very large event after Hurricane Fabian, where Hurricane Fabian induced very strong currents, maybe down to about 1,000 meters. And those currents scoured the Bermuda platform, or the shelf of Bermuda, and transported all that material that had accumulated on the shelf at a depth of about 1,000 meters all the way out here. The sediment cups, normally you see they're filled with just a little bit of material. Here, the cup was almost halfway filled. It was really exciting. So one of the focuses of my research right now is basically looking at the statistics, or basically looking at the climatology of the deep ocean, because we have a record, it's over 30 years long right now, and so we're just now have a long enough record where we can actually start to understand what the weather is like in the deep ocean off of Bermuda. Another reason that it's really important to study the Oceanic Flux program is right now we have over a 30-year record of material that we've archived of the flux. And now we can start to look at processes by reading the signals that are embedded in that material using very sophisticated analytical methods. We can begin to reconstruct how the ocean has changed over decades. And one of the big things that's changed in the ocean because of climate change, because of this increase in carbon dioxide in the atmosphere, is it has increased the acidity of the ocean. And so the change in the acidity, even though very slight, is very important. And one of the reasons that that's so important is many of the very basic producers, the primary producers, and also the microzooplankton, or the very small animals that depend upon the primary production, secrete shells made of calcium carbonate. And there's different forms of calcium carbonate, but some of those forms of calcium carbonate are already undersaturated, which means that they dissolve in ocean water right now. When you make the ocean more acidic, it increases that dissolution of the shells. That puts an enormous amount of stress on the animals that are at the very base of the food chain. The importance of having long-term records in oceanography is really multifold. We really can't understand the ocean unless we understand the ocean in its historical context. It's like understanding the history of cultures. You can't look at a culture right now and understand how it got to be that way. You need that context. And so these long-term time series programs are extremely important. The Oceanic Flux program is only one long-term time series program, although it's the longest of its kind as far as looking at the deep ocean. An example of some really important research has been what has been the effect of the Clean Air Act in the U.S. So when researchers first came out here in the 60s and measured the air and measured the ocean water, what they found out was there's an enormous amount of pollution that's being transported from the United States and Canada to the Bermuda with the prevailing winds. And part of that pollution was all sorts of things from smokestacks and also lead from leaded gasoline. And we could measure that in the ocean waters and then also measure it actually in the flux, measure it down deeper in the composition of the waters. And we can see those signals of that pollution using certain elements that are toxic elements that are in very high abundance in smokestack particles and also in the lead from leaded gasoline. You can trace where that lead came from, whether it's the US or whether it's Europe or whether it's Africa or South America, using those isotopes. One of the workhorses in oceanography is an instrument called a CTD. CTD actually stands for conductivity, temperature, and density. Those were the first things that were measured on this big contraption. Basically, the CTD has a number of sensors on it, so we can take and it's connected to a conducting wire. So as a CTD goes down through the water column, we can take a profile of a number of different very important ocean properties. One of the most important properties is temperature and salinity, as those determine what the density of seawater is and how the different water masses stack up against each other. Another property is oxygen. We can look at the fluorescence, which is basically a measure of chlorophyll, a measure of the phytoplankton concentration. We can look at turbidity, and we can look at other properties as long as those sensors are on the CTD. The other thing that's really neat about a CTD is it has a rosette of bottles. And so once we go down and we're looking at the profile of the water column, we can go, oh, we really want to take a water sample at a certain depth. But we can stop the CTD and we can send a signal down that conducting wire and we can tell those bottles to close and take us a water sample. So the CTD is a really basic workhorse in oceanography. Almost every oceanographic ship spends much of the cruises taking these CTD profiles. The Oceanic Flux mooring is basically a mooring that's about 4 kilometers long, and it is composed of an anchor at the bottom, as all moorings are. And then above the anchor we have things called an acoustic release, and so that allows us to, when we recover it, that allows us to separate the main part of the mooring from the anchor so the mooring will float to the surface. The mooring itself is composed of, from the very top, we have a subsurface buoy at 450 meters. And that subsurface buoy has some flotation on it. It also has a satellite transmitter, it has a strobe light, and it has a radio. And then we have our pieces of equipment. So we have sediment traps, the big yellow funnels at 500, 15, and 3,200 meters depth. And the 3,200 meter depth one there's been a sediment trap down there in the water at 3,200 meters depth for nearly 95% of the time since 1978, which is pretty incredible. And then we also have a current meter. So our current meter is really exciting right now. It replaces current meters that would take 3 people to carry. Right now I can pick it up with one hand. It's a little acoustic current meter. It measures the currents using a Doppler shift, which is, you can hear that right when you have the ambulances going away from you. So very low power, and we've just recently put on a CTD, so it's also got temperature, a salinity sensor, turbidity sensor, and a fluorometer. All these wires are under an enormous amount of tension, so it's extremely dangerous. So we need to know exactly how to work the equipment that's on the deck to be able to recover these moorings safely and to deploy them safely. Underneath the sediment trap, we have a carousel of bottles, and each one of those bottles rotates underneath the funnel. Every 2-week period, we program it for a 2-week period, and then collects the material that's sinking through the water column during that 2-week period. After that, we take those bottles and bring them back to the lab where we process that material under very, very clean conditions. The first thing we do is we size fractionate the material, use a set of extremely clean sieves, sieve the material, and then photograph that on gridded dishes under a microscope, so we have a digital archive of what we've collected. We're very, very careful in how we prepare our traps, and also the brine, the seawater brine that we have in those sample cups. So we have to collect that seawater brine using a special contraption, a special bottle called a GoFlow bottle. And we deploy those bottles on very clean wire, Kevlar wire that's jacketed, so it's not the normal wire rope that's filled with grease, etc. And we deploy those bottles under very clean conditions, and those bottles are very, very clean bottles. I've worked with the crew on this ship for probably 4 or 5 years now. We know each other really well. We form a great team. It's one of the most enjoyable parts of being a seagoing oceanographer, is working with the team of people on the ships.